So let us move on to the second example in cantilever beam. The beam consists of both concentrated loads as well as uniformly distributed load. So the figure shows it's having a load of 2.5 kilonewton at the free edge, 1 kilonewton per meter for 2 meter length, and another 3 kilonewton point load. How to draw the shear force diagram and bend moment diagram? So we can now move quickly as we have the concept. First, shear force calculation. Let us start from the point B. Always consider in this portion BC, if you consider a section, consider right of it. Always we consider right of section. So first I am going to write shear force at B, FB. FB is equal to the total load acting at that particular point. It is 2.5 kilonewton. Next, consider point C. At the point C, there is no point load. From C to B, C to D, it is only UDL. Only if there is point load, you have to consider just to the right and just to the left of it. So you can write here simply FC. Shear force at C is equal to, consider point C and right of it. At the point C, whatever the loads acting to the right of it, it is only 2.5. And sign I have put positive because downward load is positive. So at the point C, it is 2.5. When you come to point D, the total load acting to the right of it, the 2.5 kilonewton plus 1 kilonewton per meter acting over a distance 2. So the total load is 1 into 2 kilonewton. So shear force at D is equal to 2.5 plus that load 1 kilonewton per meter acting over a length 2. So 1 into 2. So 2 plus 2.5, it is 4.5 kilonewton. Now consider point E. At the point E, there is a point load. So you have to consider right of it as well as left of it. So FE, right. Just to the right of it, the total load is that 2 into 1, 2 plus 2.5, the same value 4.5. Just to the right of that point E. But to the left of it, if you consider a point, a section just to the left of E, if you consider a point here, total loads will be 2.5 plus this 2 plus 3. So already I can write 2.5 plus 1 into 2 plus 3. So this 4 plus 3, 7.5 kilonewton. And shear force at A. Shear force at A is algebraic sum of all the loads acting to the right of it. At the point A, consider all the loads to the right of it, that is nothing but 7.5 itself. That is 2.5 plus 1 into 2 plus 3, 7.5 itself. Okay, now we have to remember one thing. When there is no load, the shear force diagram goes horizontally. But when there is uniformly distributed load, you have to connect that points by a straight line. We'll see it now. Draw a baseline. To draw the shear force diagram, draw a baseline. Here all the values are positive. So at the first point it is 2.5. So FB 2.5. So you mark 2.5. From the baseline you mark 2.5 and write 2.5 kilonewton. Then there is no load. So draw horizontal line. At the point C, it is 2.5. That is what we have marked here. You mark 2.5, connect them, so this is straight line parallel to the base. Now FD, it is 4.5. At the point D, it is 4.5. Connect this 2.5 and 4.5 by a straight line. Okay, connect 2.5 at C and 4.5 at D by a straight line. Now FE right is also 4.5. So here 4.5. That is, since there is no load, the shear force diagram will be parallel to the base. So this is 4.5. FE left 7.5. So from here you mark 7.5. Connect it. And FA also 7.5. From here you mark 7.5. Connect it. So by looking into the diagram, you can easily draw. There is no need even for writing these steps. As a simple way you can draw the diagram now. See, at the point 2.5, so you mark 2.5, a vertical line. There is no load, so you go straight parallel to the base. Up to this point also there is no load, you have come straight up to this. Now when you come to here, it is 2.5 plus 2, 4.5. So mark 4.5, connect these two by a straight line, being UD line. So this is a straight line. And there is no load in between these two portions. So come 4.4, come parallel to this. Then suddenly there is a load of 3. So increase it by 3, raise it by 3. So it is 7.5. So this ordinate is 3. This is 3, this vertical ordinate. There is no load, so you just go straight. And this is 7.5. See, this reaction at this support is going to be 3 plus 2, 5. 5 plus 2.5, 7.5. So this vertical ordinate represents this reaction here. So this is the shear force diagram. You hash the inside of this diagram. Then mark it as positive, because all the values are above the diagram, shear force diagram. So hatch it. That's all. That is the shear force diagram. Okay. So one point which you got additional in this furnace, if there is uniformly distributed load, the shear force diagram or the shear force variation will be a straight line variation. When there is no load, the shear force diagram will be parallel to the baseline. Next we pass on to the bending moment diagram or bending moment calculations of this example. So now we are going to calculate the bending moment values. First point B. Moment at B is equal to 0, because at the free end of a cantilever the bending moment will be 0, because 2.5 into 0, that load is acting at that particular point, so it will not produce any moment. Next point MC, consider point C. At this C, consider right, there is only one load 2.5 which is acting at a distance of 0.5. So load 2.5, the distance is 0.5, so it is 1.25 kilonewton is the load into meter. Kilonewton meter is the unit of the moment. What about the sign? This 2.5, this is the load. If you rotate it about C, it goes clockwise. It produces a clockwise moment, but according to our sign convention, right of section, anti-clockwise positive. So this is a negative moment. Minus 1.25 kilonewton meter. Next point D. Moment at D is just to the right of C. There are two loads, this UDL as well as this point load. The point load 2.5 is acting at a distance 0.5 plus 2, 2.5. So minus, because clockwise moment, 2.5 into distance 2.5. This 0.5 plus 2, 2.5 is the distance. What about this UDL? We can assume it as the total load of 1 into 2. 2 kilonewton load is assumed to be acting at the center of it. This total load 1 into 2 kilonewton is assumed to be acting at the center. So this distance is going to be 1 meter. So UDL, when you take the moment for that UDL, the load is 1 into 2. It is acting at a distance of 2 by 2, that is 1 meter from D. Okay, so this works out to minus 8.25 kilonewton meter. Hope it is clear. At the point D, 2.5 acting at a distance 2.5. This 1 kilonewton per meter UDL can be treated as 1 into 2, a load of 2 kilonewton acting at the center of that distance, that is at 1 meter from here. So 2 into 1, that will be the moment, that is negative. Coming to point E, the first load 2.5 is acting at a distance 0.5 plus 2, 2.5 plus 1.5, 4 meter. So minus 2.5 into 4. Now the second load. The second load is 2 kilonewton acting at 1 plus 1.5. So the second load is 1 into 2, the load, acting at 1 plus 1.5, that is 2.5. It works out to 15. Next, moment at A will be minus 2.5. The first load acting at total distance is 2.54 plus 1, 5. 2.5 into 5 minus this load. This load is 1 into 2. The distance is this 1 meter, another 1.5. 2.5 plus 1, 3.5. So this total load is 1 into 2 acting at center. So this distance 1, 1.5 plus 1, 2.5 plus 1, 3.5. Then this load 3 acting at 1 meter. So minus 3 into 1. It works out to 22.5 kilonewton meter. So that's all the bending moment calculations. Load into distance up to the point where you take the moment. Now you can draw the diagram. For that you draw a horizontal line, which is the baseline. Now at the first point B, the moment is 0. So 0. So that point is at the baseline itself. Second one, MC. At the point C, it is 1.25. So from here you mark 1.25 kilonewton meter. There is no load in between this, so you join it by a straight line. Next point is MD. At the point D, there is 8.25. At this point, it is 8.25. From the base, you measure 8.25. Since there is uniformly distributed load between these two points C and D, this portion, these 2 points has to be connected by a parabola. You connect it by a parabolic arm. You connect it by a parabola. This portion is parabola. So this is point C. This is point D. Since there is UDL, you connect it with a parabola. Next is ME, minus 15. So along this line, from here you mark 15. There is no load between this, so you connect it with a straight line. And next A, it is 22.5. So from the base you mark 22.5 kilonewton meter, connect it with straight line. So here this portion is straight line. This is straight line because between D and E and between E and A, all these are straight lines. Only this portion between C to D. Between C to D, it is a parabola since there is uniformly distributed load. Now this entire figure is below the line. We have negative diagram. Hash the inside. Write down bending moment diagram. Hope it is clear. Only thing to remember is at the point where there is point UDL, you connect it with parabola. Now one thing to remember, when we draw it to actual scale, you remember that this parabola, the tangent to the parabola at this point and tangent to the parabola at this point should be this straight line. So this straight line should be the extension. Never draw a straight line like this, then draw a parabola like this, then a straight line like this. Never join it like that. If you take point by point, if you discretize this 2 meters into say 0.1 meter interval, and then if you try to draw this actual bending moment diagram, it should be drawn in such a manner that tangent to this parabola at this point should be this straight line. Tangent to the parabola at this point should be straight line. That is a smooth transition. It should not be like this. This is wrong. So when you draw it, see that the curves and straight lines are connected in a smooth way. So with that we finish the two typical examples on cantilever beam. In the next video we will be going for analysis of simply supported beams. Thank you.